So what is standard normal variate? So already we have seen the normal variable in Gaussian distributions, that in another language we call this the normal distribution. So now what is actually the standard normal variate? Suppose the first concept, the standard normal means it's obeys the Gaussian distributions, and standard means its mean must be 0 and its variance must be 1. Because of these things, mean will be 0, its mean will be 0 and its variance must be 1. If the distribution that follows this property, that things are called the standard normal variate. Standard normal distributions. Okay. Standard normal distribution. And in generally we denote the standard normal distributions as Z. Okay, I think you have understand this thing. Now for any distributions, the question is, for any distributions, how we will convert these distributions as standard normal distributions, and why we need to learn this standard normal distributions concept. Why actually we need to learn? So let's see step by step. So this is the first job we have. This is the first concept. Now secondly, how we will convert. Suppose let's take we have given a distributions A x that follows the any normal distributions, any with mu, mean mu and variance sigma square, that's follow any normal distributions. And the question is, how we'll convert these normal distributions to a standard normal distribution? Means we have to apply the standardizations technique to convert any distributions to a standard normal. Suppose let's take we have value of the output of the random variable x is, let's take its output is x1 to x100. It's 100. Its output is, let's take its output is this one. Okay. Now and its mean is equals to, mu, and its variance is equals to sigma square. Let's take. Now the question is, how we'll convert it. See. So to standardization technique, to apply the standardization technique, standardization is TA. Standard. Suppose we have the point on these distributions x, the point is x1, x2, x3. Suppose let's take its points, and in general its points, let's take its point is xi. And after standardizations, we have to calculate it, the xi dashed. Okay, and this xi dashed will be calculated using this formula, I minus mu by the standard deviation sigma. Using this simple formula, we have to calculate it, and this will be follows for all I. This for all I. Now this xi dashed that we have calculated from this formula, this mu is simple this mu, and this sigma means this simply the same sigma, and this xi dashed that I have calculated, that's obeys this standard normal variation, standard normal distribution, means these xi dashed are those normal 0 1 distributions. Here xi dashed is simple a standard, is this xi dashed is simple a standard normal variate. These things are standard normal distributions and these things are standard normal variate. Don't be confused about these two terms. Standard normal variate, these two things. Now the question is why actually we need to learn it to this concept, why actually we need to learn, and why these things are applicable in real world. Let's see. Suppose we have given, suppose we have anyone give a distributions of a data set x. and it's follow any normal distribution. Suppose let's take its mean is mu and its variance is sigma square. Okay, suppose let's take. Now we can easily, using this formula, we can easily convert these distributions to a standard normal distributions. Z by applying these things, Z x minus mu by simple sigma, and this Z, and now these Z's will follow. Now these Z's must be follow to the normal 0 1 distribution. Normal 0 1 distributions, it is the simple normal distributions. Any normal distribution, it will be better language. And it is the standard normal distribution. This is the standard normal distributions. Okay, now the questions is, and why these things are important. Now in previous lecture, just remember the 60, 68, 95, 99 rule. If you just remember these things, on that rule we can see that if anyone give a normal distributions, then we can, using this concept of the normal distributions, we can draw a beautiful property of this. Suppose let's take it's must be something like that. This must be like that, symmetry curve. Actually it is the normal distributions like that. Okay, and here the Picard positions must be mu, means here for the normal distributions it mu is 0 0 and first standard deviations is 1. This side will be minus 1. The second standard deviations must be 2. This side must be minus 2. Third standard deviations is 3, and this side will be minus 3. Okay, now if anyone given these things, we can easily conclude that on the range of 0 and 1, we can easily find that on the range of the 0 and 1 we have how much data on this range. How much data we have? We have 34.1% of the data on the whole data set, and on this range also we have 34.1% of the data. Means on the total range 0 to minus 1 to 1 we have 68.2% of the data we have on the range of the minus 1 to 1. Similarly, we can conclude that using this formula, we can conclude that on the range of the 0 to 2 in second standard deviations, on the range of the 0 to 2 we have how much point? We have means we have here the means is from the second, means in total this range we have 95.4% data, and in the range of the third distributions, and in the range of the third standard distributions, means in minus 3 to 3 we have 99.6% of the data. So on the first standard deviations range we have 68.2% of the data. On the second standard deviations range, that we have already seen. So the importance is that we can easily calculate, we cannot calculate it to 1 sigma, 2 sigma, just you can easily conclude that on the range of the 0 and 1 we have 34.1% of the data. But if you just convert these things on the 0 on the standard normal distributions, so on the importance of the standard normal distributions is like that, and we can easily conclude that on this range we can easily conclude that the number 1, the approximately approximately 68% of the data means observations xi dashed must be it as a dashed, don't be confused, xi and xi dashed, it must be xi dashed. Okay, lies between -1 and 1. First observations. Second observations is that approximately 95% of the point of xi dashed lies between -2 to 2. And the third observation is that approximately 99% of the point of xi dashed lies between the third standard deviations. So we have not calculated 1 sigma, 2 sigma, 3 sigma. So we have not calculated this, what is the standard deviations and from the variations. That things we have to, we have not calculated. And also there have many importance to standard normal deviations. The main importance means applications is like that. With the by simple using this is technique, 68, 95, 99% rule, we can draw easy sums and we can easily build some beautiful properties of our data sets. So this is the main interpretations, the main intuitions of why actually we need to convert this standardization technique for any distribution, for any normal distributions. Okay, not only any normal distributions, in any distributions it is possible to convert these things as standardizations, not only normal. Okay, these things are the simple technique for the standardizations technique. I think you have understood from this beautiful example, from the beautiful examples of the 68, 95 and 99% rules. I think you have understood its importance and its concept behind its concepts, and how we will convert any data sets to the standard data sets. And where we will learn the central limit theorem and in the more depth part of the probability and statistics theorem, then we will understand its importance, why these things are actually important in real life. Okay,